Hello everyone, and welcome to the presentation of this new project where we've built something that's a bit more than just a chatbot, a private sales assistant designed for a sales platform that we developed rather quickly using Django, since the assistant needs to work on a website. To carry out this project, we used the open source model Llama and ChromeAdap as the vector database. Next, we extracted all the data from the platform, I mean the sales website, and this data is stored in a SQLite database. And finally, a semantic router was implemented, which allows requests to be intelligently routed according to two different categories. We will talk more about these categories in detail during the technical presentation of this project. So, let me explain a bit about the context in which this project takes place. RF is the sales website I mentioned at the beginning of this presentation. It's a website for selling perfumes. As you can see right here, just a quick note, these images were randomly taken from Google just for the purpose of this project. We are not actually selling these perfumes. And so to get back to the explanation, this platform operates in a fairly traditional way. When a customer visits the site, they start by searching for what they want. Let's say, for example, women's perfumes. They either have to use this rather old school search bar to specify the product name or browse through all the product pages. The problem is that this is a waste of time. And every time the visitor searches using the search bar, the interface completely reloads. And this user experience is really outdated. That's why, as part of this project, we decided to implement a personalized sales assistant based on a language model that you can see right there in the lower corner of the interface. Now imagine the difference in experience. Instead of navigating through complex menus, the visitor can simply ask questions in natural language. For example, they can simply ask, "What perfumes do you sell?" I'll copy and paste the text so as not to waste your time. And the customer gets a fairly immediate answer without having to browse through all the product pages. So it asks me to log in online in order to simply access what's called an RF service. I'll explain in a few seconds why it's asking me that. There's something even more interesting, which is a hyper-realistic integrated avatar. Let me show you. So why integrate an avatar? This kind of project can really suit beauty or fashion websites because the customer experience is extremely important in these industries. This avatar represents the assistant and can even access the customer's purchase history. Now you understand why we've been asked to log in for a better service. The customer can log into their account and the assistant recognizes them personally and can recommend products tailored to their tastes and based on their purchase history. I'll give you a quick demonstration. I've created a fictitious customer with a purchase history, and we'll see what the assistant suggests to us. After this short demonstration, we realized that once the customer is logged in, the assistant specifically recognizes the customer and also understands their somewhat complex requests, and directly presents them with products that match their criteria. It's also possible to use voice commands and get a spoken response from the assistant. It's a bit like having a conversation with an in-store advisor. That's a quick overview of this presentation. This approach completely modernizes rental sites, drastically improves the user experience, and can potentially lead to a significant increase in revenue. Regarding the development approach for this project, we proceeded in several stages. The first stage was to develop the assistant, then a second stage focused on developing the website and integrating the assistant, and possibly a third and final stage, which will be the deployment of this project on AWS, because we still haven't deployed it yet. I hope that for this project the problem statement is perfectly clear. In an upcoming video, I will present the technical architecture of this solution. Thank you for your patience and see you very soon. Hello everyone and welcome to this second part of the presentation, which focuses on the technical architecture of our project. So maybe you're wondering why. The first part was simply because, as with any major project, we divided the development into several distinct phases. This allowed us to better manage the complexity of each task and also to focus more on each stage. As a result, this first part focuses on laying the foundations of our sales assistant. So, speaking of foundations, our assistant is designed to handle two very distinct types of questions. On one hand, we have frequently asked questions. Those recurring questions that customers ask, like, can I return a perfume? Or what payment methods are accepted? And on the other hand, we have product-related requests. More specific questions like, what products do you sell? Or, show me your most popular perfumes. This distinction is important because it determines how our system will process and respond to each type of request. To efficiently handle frequently asked questions, we use an approach based on semantic search. To explain a bit what semantic search is, actually it's something we use in our everyday lives. I'm talking about Google. When a user types a word or some text into the search bar, Google, the algorithm behind it, uses semantic search to provide results to the user. So what exactly happens? For example, when we type a word into the search bar, Google processes that word through a vectorization process. That is, the word is transformed into a vector, and then this vector is compared to all the topics on which Google's algorithm has been trained. These topics are also represented as vectors, and the topics that are actually much more similar. The ones that are most similar to what we typed in the search bar are then suggested to us, ranked by similarity, and what is used to determine this similarity is called cosine similarity. To show you more concretely what I'm talking about, you can simply do the following. Simply go to Google on your browser and type in hugging face. So it's this first link. First, you need to create an account. As for me, I'm already logged in because I have an account. Next, we'll go to models in the menu. And we'll filter to only display French language models. After that, go back to task and select NLP. Here, sentence similarity. So, well, I'm going to pick a model at random. I'll choose this first one. Actually, Hugging Face. It's a platform where there are many open source models. So we can use these models to run tests or for any kind of project. Here, we're going to test the similarity of a few words. Let's take, for example, the word car. We'll specifically compare the word car to automobile and vehicle, for example. You can add several other words by clicking Add Sentence, but we'll just keep these two words. You see, automobile is 87% similar to the word car, and vehicle is 95% similar to the word car. So that's exactly what happens when we type a word or some text into the Google search bar. What we type is vectorized and then compared to several topics on which Google's model has been trained. And so these topics are also in the form of vectors. And it's the topics with a very high similarity rate to what we've typed that are suggested to us in the end. And of course, this algorithm has a similarity rate. For example, it can be set at 60 or 70%, meaning that only topics with a similarity rate above 70%, for example, or 80% are suggested to us in the end. But we also have to be very careful because these models are biased, meaning they depend on the environment in which they were trained. If you take, for example, a model that was trained in an environment where words are not used in their proper context, then the similarities you obtain will be biased because they won't truly reflect the meaning of the words you provide. To give you an example, you can simply look for the similarity between the words peace and war, for example. Alright, now I'm going to pick a word at random. Bus. So why did I choose these words? When we talk about war, we often talk about peace. You'll see that these words are antonyms, but they will have a fairly high similarity. You see, peace is 60% similar to war, yet they are really antonyms. So this is one of the things that can make these models fail a bit. To wrap up this aside, I'm going to show you a bit about what vectorization and similarity are. Cosine? So let me quickly show you this project I worked on to show you what vectorization is. Actually, vectorization looks like this. For example, when you have a text, that text is transformed into a vector, which is what you see here, and this vector is then given to a model. So in our example, it's Google's model, and this model will compare it to other topics in its database. And finally, it will suggest everything that is similar to what we typed. So to vectorize a word or a text, we have several methods. To perform vectorization, we also talk about feature extraction. So we have several ways to do vectorization. These include label encoding, one-hot encoding, n-gram, TF-IDF, and word embedding. I'm not going to explain how each vectorization method works because that would make this video quite long. But in the context of our project on the sales assistant, we used word embedding, the last method, also called sentence embeddings, to perform vectorization. Finally, this is what cosine similarity looks like. Here we want to see how often the materials, that is putty and board, are close to the group glue and adhesive. So what we do is first vectorize the words putty and board using word embeddings or sentence embeddings. To make things much simpler, we use 2D coordinates. But in reality, these vectors are of size 300. So good luck to you if you want to represent 300-dimensional vectors. And we represent each word in the plane, which you can see right there next to it. Then we look at the angle that separates each vector. Here we have the angle between the words putty and adhesive color. Here is the angle between board and adhesive color. And in the end, we calculate the cosine of this angle. And the number we get represents the similarity between the word we enter and the word we want to compare it with. The larger the angle, the lower the similarity, and the smaller the angle, the higher the similarity. Now, after explaining what semantic search is, to get back to the project, what we do is collect all the questions from our website. In fact, I want to talk about these questions that you see displayed on the site. Excuse me, give me a few seconds to show them to you. There, right here. And so we organize these questions and answers in a structured file. In our case, it's a CSV, and of course, there aren't just these questions. We've collected much more than that from other perfume sales websites. Next, we transform this data into vectors and store them in ChromaDB. It's a vector database specifically designed for semantic search. The technical trick here is that we generate vectors only for the questions, not for the answers. The answers are stored as metadata, which allows us to optimize our semantic search process. For product management, we take a slightly different approach. Here, we collect product data directly from the source, from the site's catalog, so each product comes with its detailed information such as price, description, rating, and more. Then this data is stored in a SQLite database, which is perfect for this type of application because it's lightweight. It's fast and ideal for structured queries. This approach allows us to later perform complex searches on products, such as filtering by price, by category, by rating, everything customers need to find the perfect product. Now, here is the core of the system, the complete architecture of the personal sales assistant. So everything starts with a semantic router. So it's this router that analyzes each customer question and intelligently determines whether it's a frequently asked question or a product request. If it's a frequently asked question, the system queries our database. ChromaDB finds similar questions using semantic search, retrieves the answer stored in the metadata, and passes it to the LLM, which generates a natural and personalized response. And if it's a product request, the process is different. The LLM transforms the question expressed in natural language into a precise SQL query. This query is executed on our SQLite database, and the results are reformatted by the LLM in natural language. So in this diagram, I haven't included the use case for the avatar. To have the avatar, we used an API from iGen. iGen is a platform that allows you to make videos or presentations using AI or avatars. So in the case where the client uses the avatar instead, the entire process remains unchanged up to that point. The responses are sent to the avatar and the avatar simply repeats them. Here's an example to better explain the queries applied to our SQLite database. For example, a client might ask, "Show me all your best products with a price under 80 euros." What happens is that our LLM, the model we use, will analyze this request and automatically turn it into an SQL query. Here is the SQL query that corresponds to this question. Next, this query is executed on our SQLite database to get the result, and finally, the result is delivered to the client in natural language. Now, let's move on to the second part of the project, which is the development of the website. So I should point out that I am not a web developer. The goal of this presentation is to focus much more on the assistant that was designed using LLMs and by doing RAP. These are areas within data science. So for this part, I will only cover the main points, so this will be very quick. So to create the website you saw earlier, we first started by building the front end using HTML5 and CSS3 to create that clean and professional design. There's also some JavaScript to handle the interactions between the chatbot and the user. Then for the backend, we used Django, a Python framework that provides an architecture perfectly suited to our project. I want to talk about its modular structure. During development, we organized the application into separate modules: catalog modules for product management, payment modules for transactions, chatbot modules for our assistant, and so on. Next, on the database side, we used SQLite for development and storing our products. Finally, the architecture is enhanced by integrating external services, such as Amoa for the conversational intelligence of our assistant agents, to create a virtual avatar that humanizes the experience Stripe for credit card payments, and PayPal to offer alternative payment options. Finally, the third and last part, deployment. Up to now, we still haven't deployed the project as we plan to make even more improvements, but we are considering deploying it on Amazon Web Services. This brings us to the end of this presentation. Thank you for your attentive listening and see you soon for more projects.